Our next section is Fourier Series and we'll be dealing with continuous time Fourier Series. It is an interesting subject and it is more interesting if we understand the derivations. Since we don't look at the derivations, we need to remember the equations. This section has 5 subsections. We'll start with the first of them, Introduction to Fourier Series. We have dealt with exponential signals in the first section. Now we see the exponential signal as an input signal to an LTI system. What happens is interesting. If you put the exponential signal into an LTI system, e power st as the input signal, what we get the output doing all this calculation, we get the output as lambda times e power st, which shows us that e power st is an eigenfunction with an eigenvalue of lambda, where lambda is a complex constant. Using the result in the last slide and using the convolution equation, which in both cases gives you y of t, we arrive at this conclusion, this result, y of t equals h of s times e power st. So our eigenvalue is h of s, which we define as frequency response. And this frequency response is a function of the impulse response h of tau or h of t. What is the FSR of CT periodic signals? Oh, it is Fourier series representation of continuous time periodic signals. So we know the condition for a signal to be periodic, which is x of t equals x of t plus capital T, where capital T is the fundamental period. Well, any periodic signal can be represented as a Fourier series representation if it satisfies the Dirichlet conditions, and this Fourier series representation is given below here. Now, any signal, any periodic signal can be written as a summation of a constant times complex exponentials, which I'll read it out as x of t equals summation k tending from minus infinity to plus infinity ak times e power jk omega naught t, where k can take values from minus infinity to plus infinity, and omega naught is the fundamental frequency of the periodic signal. Now, any periodic signal x of t can be represented using this expression, which is called the synthesis equation, and below we can find the coefficients of these complex exponentials. The expression for these coefficients is known as analysis equation, which is given by this expression. We move on to the next subsection, Fourier series and LTI. In the last subsection, we have derived this equation and we have seen that lambda is a complex constant. Now S is given by sigma plus j omega, but in Fourier series representation for continuous time, we take sigma equals 0. So which leaves us with S equals j omega. And using the frequency response equation, we find that if an exponential function or an exponential signal is fed to an LTI system, we find that the output signal is an eigenvalue times the eigenfunction, that is the frequency response times the exponential function. We know that any signal x of t can be represented using this equation, and now when we give this to an LTI system, what we get is an output given by this equation. And for S equals j omega, we get the Fourier series. In order to find the Fourier series representation, after doing all these steps, we come to the conclusion that any periodic signal x of t can be represented using summation of complex exponential multiplied by their coefficients, and their coefficients are given by this equation. These two equations are very important to solve problems related to Fourier series. Well, there's a lot of text, but the conclusion is that any signal, any periodic signal which has an FSR or Fourier series representation, it'll have an energy which approaches to 0 as n tends to infinity, where x of n is given by this expression. Now, what about the points where this signal is discontinuous? Well, at these points, the infinite series converges to the average of the values on either side of the discontinuity. Do all periodic signals have an FSR? Well, there can be cases in which AK or the coefficients need not be well defined or xn of t need not converge to x of t. Well, what are these conditions? These conditions are discussed in the next subsection, which is Dirichlet conditions and Gibbs phenomenon. For any signal to have an FSR or Fourier series representation, it needs to satisfy these three Dirichlet conditions. Well, the first condition says that it has to be absolutely integrable over a period. That is, it has to satisfy this inequality. Well, the second condition says that in a finite interval of time, there should be a finite number of maxima and minima. The third condition says that in a finite interval of time, there are only a finite number of discontinuities, and each of these discontinuities is finite. Does this signal have a Fourier series representation? Well, no, because it violates the first Dirichlet condition. This signal is not absolutely integrable over a period. This example is also not having a Fourier series representation because it violates the second Dirichlet condition. It has infinite number of maximas and minimas in a finite interval. This example also violates the third Dirichlet condition because it has infinite number of discontinuities in each period. Now let's consider a rectangular signal. Well, calculating the coefficients, we find that for k equals 0, the coefficient is given by this expression, and for k not equal to 0, it is given by this expression. Well, the question still remains how we have reached a rectangular pulse using a summation of complex exponentials. This slide explains it. Considering only one term in the Fourier series representation, we would find something like this. A few more terms, we would get a graph like this. A few more terms, a few more terms, a few more terms, which converges to the rectangular signal. You can think of this rectangular signal as the summation of all these sine curves with different frequencies added. Gibbs phenomenon at the discontinuity says, as the number of terms in the Fourier series representation increases, the ripples in the partial sum becomes compressed towards the discontinuity, with a peak amplitude of the ripples remaining constant independently of the number of terms in the partial sum. The next subsection is properties of continuous time Fourier series. Linearity says that if a signal x of t has a Fourier series coefficient ak and y of t has Fourier series coefficient or fs coefficient bk, the Fourier series coefficient of ax of t plus by of t, where a and b are constants, will be ck equals a times ak plus b times bk. Time shifting property says that if x of t has a fs coefficient ak, then x of t minus t naught will have a Fourier series coefficient e power minus jk omega naught t naught times ak. Time reversal property says that if x of t has fs coefficient ak, then x of minus t has fs coefficient a of minus k. And we find that if x of t is even, then a minus k equals ak. And if x of t is odd, a minus k equals minus of ak. Time scaling property says that if x of t has fs coefficient ak, then x of a times t, where a is a constant, also has the same fs coefficient ak. The multiplication property says that if x of t has an fs coefficient ak and y of t has an fs coefficient bk, then x of t times y of t has an fs coefficient h of k equals the convolution sum of a and b. Now, if x of t has a Fourier series coefficient ak, then the conjugate of x of t will have a Fourier series coefficient, the conjugate of a minus k. The differentiation property says that if x of t has an fs coefficient ak, then dx by dt will have a Fourier series coefficient jk omega naught ak. Here we need to note that the magnitude of the kth harmonic is amplified. Hence high frequency is amplified more than the low frequency. Parsel's relation for continuous time periodic signal relates the power of the signal and the Fourier series coefficients, and it is given by this expression. Our next subsection is filtering. Let's understand the concept of filtering with an example. Think about an RC circuit. Well, this differential equation represents the RC circuit system. For the input voltage Vs given by this expression and the output we find as this expression, we find the Fourier transform for the system as 1 by 1 plus RC j omega. Now that we have got the expression for frequency response, we plot the magnitude of frequency response against omega and phase of frequency response against omega. Well, what we observe in the magnitude versus omega graph is we could restrict or limit the frequencies that contribute to the frequency response. Well, this is called filtering. An ideal low-pass filter allows only low frequencies to pass through the system. As you can see here, the frequency response has the value of 1 for low frequencies and 0 for high frequencies. A high-pass filter is opposite of the low-pass filter. It allows only the higher frequencies to pass through the system. As you can see here, the frequency response value is 0 for low frequencies and 1 for high frequencies. Thereby, higher frequencies contribute more to the frequency response. A bandpass filter allows only a group of frequencies to pass through the system, hence contributing to the frequency response. Here you can see the frequency response has a value of 1 for a group of frequencies and 0 otherwise.